Welcome to today class of nonlinear vibration. So, in the last few classes we are discussing about the application of the nonlinear vibration systems what we have studied in our earlier classes. So, we are discussing about the response of the nonlinear systems and their stability. So, initially we have studied about the free vibration response of nonlinear systems. Now, we are continuing with the force vibration of nonlinear systems, in which we have discussed about the single degree of freedom systems and multi degree of freedom systems also. So, in multi degree of freedom system, so we have just discussed about a few degrees of freedom system, but nowadays many systems which can be obtained by analyzing the finite element methods will contain a large degrees of freedom system, and the matrix size or the equation motion will be n dimensional, or it will contain large number of equation motions. So, in those equation motion, if nonlinear terms are present along with the boundary conditions and also the loading vectors, then analysis of those systems cannot be, we cannot discuss the analysis of those systems by the systems what we have studied before. So, in such cases, so we have to use some modal reduction method or model reduction method, and we have to discuss some other techniques to solve those systems. So, today class we are mainly focusing on the study of the multi degree of freedom systems, where we will discuss about the method of model reduction. Then, so in which we will discuss about this mode superposition method, dynamic substructuring method and component mode synthesis, and the solution we will see by using this harmonic balance method. So, we will use this harmonic balance method what we have discussed before to find the solution of the system. So, this harmonic balance method can be used along with this mode superposition method. Also, it can be used with this dynamic substructuring and component mode synthesis method. So, the analysis what we are going to study today, so it is adapted from the PhD thesis of, that is, experimental and numerical studies of mechanical systems with localized nonlinearity, which is carried out by Dr. Praveen Krishna Iyer of IIT Madras, which is submitted in 2011. So, if we have a system multi degree of freedom system with several nonlinearities and also boundary conditions and external forcing conditions, then in that case we can use this finite element method to write the equation motion. For example, let us take, we can have many different type of structures. Also these systems can be used for solving the system with localized nonlinearities. So, we can, let us take a simple structure what we have seen in the last class also, where we have taken a simple spring mass system. So, this is a simple spring mass system. So, here we can make the spring nonlinear, and so this spring can be made nonlinear, this spring can be made, or all the springs can be made nonlinear, and in that case, and this nonlinearity may be of quadratic or cubic type. So, in that case we can write this equation with 2 degrees of freedom system only, but if we have a system, let us take a cantilever beam. So, in this cantilever beam, so let it supported by some spring. So, in this case on okay, so it is supported by some spring and applied by some load. So, in this case this cantilever beam, as it is a continuous system, so this can be modeled as infinite degrees of freedom system. Also one can take in finite element formulation. So, for transverse deflection of the systems one can, so for each node, if one take a beam element, then for each node one can take this displacement and slope as degrees of freedom. So, for the ith node, so one can write this is the displacement I and slope, that is del w by del x. So, at I similarly, so it will be at j node w j and del w j by del x. So, displacement and slope one can take as the degrees of freedom at this node. So, for each element it will have 4 degrees of freedom. So, taking several elements, so one can if one take 10 elements, then the assembled matrix will contain assembled mass matrix, stiffness matrix will contain 40:40, or the size will be 40:40. Similarly, if one can take a sandwich beam, so let us take a sandwich beam. So, in which we will have, so this is the skin layer, and so this is the skin layer. If we are considering only 3 layer, this is the core, and this is the, so this is the top skin core, and this is the bottom skin. So, in this case one can take the classical theory. So, if one can take the classical theory, then one can write the displacement of top, bottom and core to be same in the transverse direction at a particular section. So, one can write, or if one take the higher order theory where taking a flexible core, if the core is flexible, then in that case the displacement of the top and bottom layer, the transverse displacement of top and bottom layer will be different. So, in those cases, so when one is taking classical theory, so one can take for one element, so one can take this W as the deflection, W as the Wi is the deflection, then del W by del W I by del x as the slope. Then one can take this Ui as the Ui is the axial displacement. Similarly, for the jth node one can take Wj del W by del x, or theta j, Wj, theta j and Uj. So, in this case one can have, one can for element one can have 6 degrees of freedom, and taking number of elements. So, it will be multiplied by this number, and one can get a matrix or elemental matrix or the assembled matrix of large size. Similarly, in case of the flexible core sandwich beam, so as the top and bottom skin deflection will be different. So, in that case at the ith node one can have Wt, then so one can write this Wt, Wb, then theta, so one theta t, theta b, and then u. So, these are at the ith node. So, in case of I, so it will be reduced to, so at the ith node one will have this 4, 1, 2, 3, 4 and 5 degrees of freedom. Similarly, at jth one can have this 5, again 5. So, 10 degrees of freedom system for element, and then in that way taking several elements. So, one can find the number of equations motion, a large number of equation motion. So, when one has a large number of equation motion, so in such cases, so one has to use this model reduction technique. So, in this case, in case of the cantilever beam, so if one use this Euler-Bernoulli beam theory, only you can write. So, the equation is linear, but taking a large deflection one can have nonlinearity present in the system. Also, when taking a force, so this force may be periodic or aperiodic. So, if one take this force at this node, so this force may be concentrated, or this force also may be, so this force may be uniform distributed, or the force may be, so one can have a moving load type of force. So, this force may be that of a moving load. So, in all such cases one has to write the equation motion with this external force taking into account. So, let us have a generalized equation motion. So, this generalized equation motion in such case can be written in this form: mx double dot plus cx dot plus kx plus fp. Fp is the force containing this x dot and time varying force. So, this may be that of a parametrically excited system also, when it is a function of time and x. Then this is the nonlinear term. So, one can write this nonlinear term also. So, with this So, this is the external force. So, this is the external force acting on the system, this is the nonlinear force we are taking, and this is the localized force, localized parametric excitation force, which is defined in terms of displacement, velocity and time, and then this is the stiffness. So, this is the force due to stiffness, and this is the damping force, and this is the inertia force of the system. So, these are the forces acting on the system, and one can write the equation motion by using any method including this finite element method. So, this equation can be of n cross n, where n can take any dimension. So, now this n dimensional equation, where this mass matrix, stiffness matrix and damping matrix are of n cross n size, and these are the vectors with n cross 1. So, one can write now using this mode superposition method, which is the simplest one, reduce the size of this equation. So, this equation can be reduced to that of order m, where m is very less than n, by using this right and left eigenvector of the linear system, taking the linear system m x double dot plus k x equal to 0 and a equal to m inverse k. So, one can find the eigenvalue. If the matrix are unsymmetrical, one can find this left and right and left eigenvalues and eigenvectors. One can find this left and right eigenvectors of the system corresponding to the eigenvalues. So, after finding these left and right eigenvectors, so one can use those things in this equation. So, taking this x equal to u r z, taking x equal to u r z and substituting in this equation. So, one can write m u r z double dot plus c u r z dot plus k u r z plus then other terms equal to, so this f t. Now, pre multiplying that thing by u L transpose. So, we have this equation. So, by pre multiplying this equation, so we have the equation u L transpose m u r z double dot plus u L transpose c u r z dot plus u L transpose k u r z plus u L transpose f p z z dot t plus u L transpose f n z z dot equal to u L transpose f t. So, here one can note that when the matrix is symmetric, so u r will be equal to u L, and if it is unsymmetric, so we will have this left and right eigenvectors. So, from the properties of these eigenvectors, so one can know that these will reduce to. So, by taking let us take m mode. So, if you are taking m mode, then it will reduce to size m cross m. So, by taking only first few modes, let us take only 2 modes, then this equation will reduce to that of 2:2. But the disadvantage of this thing is that, so while calculating, while these matrices left side it is reduced to, so these 3 reduced to 2:2, this forcing vector, this nonlinear terms and the forcing vector will. So, during simulation, so one has to find these modes, and it will rotate between, or it will rotate between the physical coordinate and the modal coordinates. So, for this nonlinear terms, these forcing terms, so when we are multiplying this thing, so these transformation, so these transformations now will contain the modal vectors. So, this is the disadvantage of this method, and in this way we can reduce the n dimensional equation to m dimensional equation. So, the nonlinear function forms a few physical coordinates to all modal coordinates. So, it will move between this modal coordinate and between the physical coordinate and the modal coordinates. So, now we can use another method which is known as dynamic substructuring. So, in which we can divide this mass matrix, stiffness matrix and damping matrix by using the slave and master degrees of freedom. So, here we can use the degrees of freedom where the nonlinearity is present and where the external load is applied. We can take those nodes or we can take those degrees of freedom as the master degrees of freedom and all other degrees of freedom as the slave degrees of freedom. So, we can take the degrees of freedom where the nonlinear terms are present, where the nonlinearity is present and where external loads are applied as the master degrees of freedom and all other degrees of freedom as slave degrees of freedom. By taking that way, so we can write the mass matrix, damping matrix and stiffness matrix this way. So, we can partition these mass matrix like this. So, we can partition the mass matrix as M S S, that is with slaves, then M S M and M M S and M M M. So, these contain all the master coordinate or master degrees of freedom, these contain all slave degrees of freedom and this is a coupled between these master and slave degrees of freedom. Similarly, the damping matrix can also be partitioned by the slave and master and stiffness matrix also can be partitioned by slave and master. And while partitioning this thing, we should take note of the thing that this nonlinearity and external loads would be in master degrees of freedom and all other degrees of freedoms will be in the slave degrees of freedom. So, now taking this or dividing this mass, stiffness and damping in this master and slave form. So, we can write the original equation. So, our original equation, this m x double dot plus c x dot plus k x plus f p plus f n equal to E f external in this form. So, by substituting this thing we can write our equation in this form, that is, so it is partitioned now and so here this is x s, also this is partitioned x s and x m. Okay. So, here it may be noted that the parametric term, so the terms associated with this x m dot and t can be written. So, in this form, as we are putting all these things in master degrees of freedoms, only the lower part will contain this thing. So, the upper part where slave thing is there. So, we are putting that thing equal to 0. Similarly, for this nonlinear term, so this is in the master degrees of freedom and slave degrees of freedom we are putting equal to 0 and this is the external loading. So, this is the external loading of the system. So, we can write the original equation in this way by taking the master degrees of freedom and slave degrees of freedom and we can partition and we can write this equation in this form. So, now by writing in this form, so we can solve this equation by using different method. Another method what we can use. So, in the previous two equations, so the nonlinear terms when we are using this modal reduction method, the nonlinear terms forcing vector rotates between the physical parameter or physical coordinates and the modal coordinates. To avoid that thing, so one can use this component mode synthesis method. So, in component mode synthesis method, a Craig-Bampton type substructure with more number of degrees of freedom represent using generalized coordinates, while the other substructure with nonlinearity is modeled with physical coordinate. So, we can use a substructure technique. So, we will use two different types of substructure in which we can use this generalized coordinate and physical coordinate. That means, in this type of thing, so we can use both generalized coordinates and physical coordinate. So, we will keep for the nonlinear terms the degrees of freedom associated with nonlinear terms, we will keep them in the physical coordinate and the other terms we will keep or write them using these generalized coordinates. So, initial physical coordinate can be transformed to the generalized coordinate by using different techniques or by using some methods. So, that thing we will discuss here. So, here we will have a slave system. So, as we have discussed before, we will have a slave and master degrees of freedom. So, in case of the slave degrees of freedom, so here initially we have divided our structure into two parts, one with generalized coordinates, another with physical coordinates. So, initially we have this all with generalized coordinate or physical coordinate x, and we can replace them by the generalized coordinate u in this way. So, let us take only the undamped and undamped linear system. So, in case of the undamped linear systems, we can write the equation in this form m x double dot plus k x equal to 0. So, here we have taken only this one, that is the slave part. So, in this case this, so I represent the interior coordinate and j represent the junction degrees of freedom. So, we can partition this stiffness and mass matrix substructure into interior and junction degrees of freedom. So, these are interior degrees of freedom and j represent the junction degrees of freedom. So, the normal mode of the above system found using eigenvalue analysis, the physical coordinate of the slave system are transformed into a set of normal coordinates u1 and the degrees of freedom x j using the transformation. So, x j is the, so this is the junction coordinate and u is the, so we have taken this u is the normal coordinates. So, we can write this psi. So, we are using this. So, this x I 1 and x j 1, I is interior degrees of freedom and j is the junction degrees of freedom. So, we are using this 1 for the slave part. So, this will be equal to phi r psi 0 I into u I 1 and x j 1. So, here psi equal to minus k I 1 inverse into k I j 1. So, this 1 for the slave system. So, in this way we can write this equation in this form. Then we can write this m 1. So, here, so we have written in this equation this m 1 1 or m 1 can be written so the mass, stiffness and damping matrix of the slave system 1 are transformed into new coordinate system. So, we can transform them into the new coordinate system u I 1 and x j 1 in this way. So, we can use this coordinate transformation. So, this into, so this is the mass matrix into this. Similarly, for the stiffness matrix also. So, we are using, so this is the left eigenvector and this is the right eigenvector. So, using the left and right eigenvector. So, we can write this, and for the damping also we can write, and for the force also we can write this way. So, now for the master system, similarly for the undamped and unforced equation of the master system can be written using this mass matrix and stiffness matrix. So, these two represent the master system and one was for the slave system. So, in this master system we can write, so as we are not changing the coordinate, so of the master system, so they are transformed to this new coordinate system by this I 1. So, I 0 and 0 I. So, I is the identity matrix. So, this identity matrix is used for this transformation to keep the procedure of the component mode synthesis same as that for the slave system. So, in this way, so we can write or we can replace this x coordinate in terms of this u coordinate. So, here x j is the junction coordinate. So, now for the similar to the slave, for the master we can write this or we can transform this x coordinate to the u coordinate system, or we can write this m 2 in this form. So, this is 0 I 0 0 1 transpose, this is the mass matrix into I 0 0 I Similarly, this is the forcing function can be written with by multiplying this transpose of I 0 0 I. Similarly, this is the K 2 and this is for the nonlinear force and this is for the external force and this is the damping matrix. So, this is the damping matrix. So, it is changed in this way, damping master matrix. So, this is the stiffness master matrix and this is the mass matrix of the master component. So, here x j, so we are taking this x j 1 equal to x j 2. So, by taking this x j 1 equal to x j 2, so we can replace this u y 1, x j 1, u j 2 and x j 2 to this form. That means, by writing this is equal to S u, where S can be written this. So, here u equal to u y 1 x j 1, as we are putting x j 1 equal to x j 2. So, we can write using this x j 1 then u y 2. So, this is a 4:2. So, this is 4:3 matrix and this is 3:1. So, finally, this becomes 4:1. So, this is u I 1 x j 1 u I 2 x j 2. So, we can replace this vector by u I 1 x j 1 and u I 2. So, writing this way, so we can now write this nonlinear force in this form. So, F n equal to S into F 1 1, F j 1 and F I 2. So, this is for the slave component, this is for the master component and the middle one is for the junction force. So, which is equal to 0 0, F 1 2 and F j 2. Similarly, we can write F in this form using this S matrix and the mass matrix and the transformed mass matrix and damping matrix and the K matrix can also be written in this. So, here you may note that this becomes the diagonal matrix. So, here M equal to S transpose M S, C equal to S transpose C S and K equal to S transpose K S. So, our equation reduced to this form, that is M u double dot plus C u dot plus K u plus F e plus F n equal to F. So, it has reduced to this form and so now after it is reduced to this form. So, one can write this where this M equal to M S S and M S M and this is equal to. So, this is similar to the dynamic substructuring what we have studied here. So, one can reduce, but in this case it may be noted that in this equation. So, the size of the matrix can be reduced very much. So, by using this modal method, so you can reduce the size of the matrix to the required level of the equation motion. So, and here also it can be noted that by this method, so while the stiffness matrix is uncoupled, both the mass and damping matrix are coupled. So, here the stiffness matrix is uncoupled K S S and K M M, but the other matrix are coupled. So, here we are using this U S and U M. So, U S will be the slave displacement degrees of freedom and so this U will be equal to. So, we will have this U S and U M. So, where U S is the slave displacement degrees of freedom and U M is the master displacement degrees of freedom. So, slave degrees of freedom consist of only the included modes of the substructure 1 and the master degrees of freedom consist of the boundary degrees of freedom and the physical degrees of freedom of the substructure 2. The mass matrix M S S and K S S will be diagonal because they are represented in the natural mode. So, this mass matrix M S S and K S S are, so they are diagonal. So, M S S and K S S are diagonal. So, as they represent the natural modes. So, in this way first one can reduce the equation motion to a required degrees of freedom instead of use very higher degrees of freedom. So, after reducing this equation to the required level, for example, if one reduce the equation to a 2 degrees of freedom or 3 degrees of freedom, then one can use the methods what we have studied, or one can use the perturbation methods what we have studied earlier to find the solution of the system. And but for higher degrees of freedom, when it is of higher degrees of freedom, then it will be difficult to apply those perturbation methods, but one can still use this perturbation method by using some symbolic software. And now, let us see, or we will use this harmonic balance method. So, now we will use this harmonic balance method, or we will describe this harmonic balance method what we have studied in our module 2 again to use this thing in this method to find the solution of the system. So, here while using this harmonic balance method, so we will discretize this, or we will write this equation, this displacement vector x k in terms of different components, different harmonics. Also we can write this forcing term, this forcing term which is a function of time, or the forcing term like the parametrically excited term. So, this x dot, or this the terms with concentrated loading, or terms with loading vector, or the terms with nonlinear terms. So, this is the terms with nonlinear terms. So, we can expand them in terms of different harmonic terms by using this harmonics. So, for example, x k, that is kth displacement, we can write equal to x k 0 plus x k L cos L omega t plus x k L sin L omega t, where L varies from 1 to n. For example, n equal to 1. So, it will be x k 1 cos omega t plus x k 1 sin omega t. Similarly, for higher modes, it will be x k 2 cos 2 omega t plus x k 2 sin 2 omega t. So, in this way, so we can write the terms with different up to certain level of frequency. So, for example, we can take only the 3 modes. So, in that case L will be equal to 3. So, in addition to this constant term, so we can have 3 more terms, 3 plus 3 6 more terms in this expansion. And similarly, for the forcing term also we can write f k equal to f k 0 plus I equal to 1 to n f k L cos L omega t plus f k L sin L omega t. So, this is for the generalized force. If we have a generalized force, so then we can write that generalized periodic force in terms of these harmonic forces. Similarly, in case of these nonlinear terms, we can also write the nonlinear terms using different harmonics, where k 0 is the constant part of the nonlinear terms and these contains the harmonic. So, if the nonlinear terms are periodic, then we can write using these harmonic terms, and so this represent the loading vector also. So, the loading may be a static loading, or it can be a loading with periodic force. So, in that case of static loading, we can use this f p k 0, and in case of periodic we can write using different harmonics. So, now using different harmonics, so one can use this mode synthesis method, or dynamic substructuring method, or this component mode synthesis method to write these equation motion, or substitute these equations in those equations, and one can, for example, so in original equation by substituting these equations, so one can write, or that equation will reduce to this form. So, where this R gamma is a residue. So, this equation is reduced to this form, that is E I j. So, where E 1 1, E 1 2, E 1 n. So, these are the x 1 x 2. So, here we have this x, these x terms are there. So, it will be x1 bar, x2 bar, xn bar, and these are the forcing term. So, this is the parametric forcing, this is the nonlinear terms associated with that, and this is the external force. So, we have taken all the force to this left hand side and substitute these equations in the original equation, and as these are approximate solutions we have taken. So, the right hand side will never be equal to 0, but there will be some residue part to this. So, this residue is retained by writing this R gamma. So, this equation reduced to this form, where this E I j equal to, so E I j equal to K I j 0 0. So, this reduced to a tridiagonal form. So, K I j minus omega square m I j. So, the diagonal term one can see, this is K I j, this is K I j minus omega square m I j. So, then here we have this minus omega into C I j, this is from the damping term, and this is from this mass matrix, and this is the stiffness. So, when we are substituting these modes, or when we are substitute these harmonics, then from that harmonic by differentiating twice. So, we have this minus omega square term coming into there. So, here we have this damping term, then this is the K I j minus omega square m I j. So, so for example, E 11. So, E 11 will be equal to K 11, and this will be K 11 minus omega square m 11, C 11 minus omega C 11, K 11 minus omega square m 11. So, in that way, so one can write this matrix. So, E I j will contain, or E I j terms will contain this way. Similarly, so one can minimize this residue. So, the residue, one can minimize this residue by using this method, or one can minimize this residue. So, this is the residue. So, integrating this residue 0 to 2 pi by omega. So, that is one cycle. So, taking this n equal to 1 to m and multiplying this R gamma with 1 cos n omega t sin n omega t dt. So, one can minimize this residue, and minimizing this residue, this equation will reduce to this form. So, it will reduce to y x a plus f p plus f n bar minus f bar equal to 0. So, where y equal to this. So, y equal to E 11, E 12, E 1 n, E 21, E 22, E 2 n, and E n 1, E n n. So, one can obtain this equation, which is a set of algebraic equations, and the set of algebraic equation can be, so the set of algebraic equation can be solved by using different methods. For example, one can use this Newton-Raphson procedure to solve this set of algebraic equation. So, instead of solving this n dimensional equation using this Runge-Kutta method, or using this Runge-Kutta method. So, one can use this Newton-Raphson method, because this Newton-Raphson procedure require the calculation of this Jacobian, and which will converge very fast. So, instead of using this ODE, so if one use this MATLAB, then one can solve this differential equation by using ODE 4-5, which is 4th and 5th order Runge-Kutta method to solve those equation, but solving this large degrees of freedom system. So, it will require huge memory and space and computational times also. So, one can, instead of doing that thing, so one can solve this equation. So, this reduced equation, which are set of algebraic equations, and one can get the solution very fast. So, while using this Newton-Raphson method, one required this Jacobian matrix. So, the Jacobian matrix, this is the Jacobian matrix which is required, or which is to be evaluated is in each iteration. So, this is the So, this is the Jacobian matrix which is required to be solved in each iteration, and this is equal to J equal to del y x a plus f p plus f n bar minus f bar by del x a. So, solving this thing, so one can find the equation or one can find the response, that is response amplitude x a of the system for different system parameters. Similarly, one can use this dynamic substructuring with this harmonic balance method also. So, in dynamic substructuring we previously we have seen that we can divide the structure into slave and master, where the slave coordinates can be retained using this generalized coordinates and the master coordinates or master degrees of freedom can be kept using these physical coordinates. So, we have a set of generalized coordinates and physical coordinates. So, by using this dynamic substructuring, so we initially we obtain this equation, and after getting this equation, so what we can do? So, we can apply this method of harmonic balance to reduce this equation to so in this case, so in dynamic substructuring, okay. So, initially in dynamic substructuring we have divided the system into the slave and master components, and here also by using this harmonic balance method it can be reduced to this form. So, which can be solved using this Newton-Raphson method to find the solution. Similarly, in component mode synthesis, so in component mode synthesis we are dividing the system into slave and master, where the slave systems are retained in terms of the generalized coordinates and masters are retained using these physical coordinates. So, after getting these equations, now we can find or we can use this harmonic balance method, and by using this harmonic balance method, so we can find the equation. So, this is the equation we can obtain, where H I can be retained in this form, and solving this, where H I retained in this form, which contain this term B I and which can be obtained from this equation. So, where these are the terms. So, by solving this algebraic equation, so one can find the solution of the system. So, in this way, so one can use this harmonic balance method in these three cases, that is mode synthesis or modal reduction method, dynamic substructuring method or component mode synthesis method, to reduce these equation to a set of algebraic equation, and those equation has to be solved to obtain the response of the system. So, after getting these response of the systems, one can study the response of the system for different system parameters, and one can study the effect of the nonlinearities or effect of forcing, damping, nonlinearities in the system. And one can take these exercise problems to exercise problems which have been. So, for example, take this system. So, one can take this system with we have a 2 degrees of freedom system, and here we have this, these are the nonlinear stiffness we have given. So, this is M1, this is M2. So, this K1 can be taken as, so this is K1, so this is K1x 1, so this is x2. So, here one can take K1 x1 plus K2 xq cubic nonlinearity. Here also one can take this cubic nonlinearity, and one can write this equation using this K2. So, the displacement will be x1 minus x2 plus, so let us write this is equal to epsilon k1 x1 q. So, this is k2 plus epsilon k2. So, this term can also be written as epsilon k2 x1 minus x2 cube. So, taking this nonlinearity, one can, so let a force is applied here. So, this force equal to F sin omega t. So, one can write the equation motion, this is very simple equation. So, one can write the equation motion and use the method, and as the force is applied to the second mass, one can reduce this thing to that of a single degree of freedom system by taking only the modal matrix of the second mass, or and one can write a single equation to find the equation motion. Next, one can take a physical or a cantilever beam with springs attached here. So, let the spring is nonlinear spring. So, here it is equal to k 1 x plus k 1 x plus k 2 x square. As one can take multiple degrees of freedom here, so one can use a finite element method to solve these problems. So, by taking 10 elements, one can write the equation motion, add this nonlinear spring to the system, also add a external force that is equal to P sin omega t to solve the system. Also, one can take a system, a belt system, so this is a belt in which a mass is placed on this, and okay. So, in this case, so this is a nonlinear spring k 1 x plus k 2 x cube, and here the damping. So, here the damping term one can take as that of a Coulomb damping. So, in case of the Coulomb damping, so it will be equal to, it depends on the velocity. So, if one plot this x dot, so this is equal to f. So, this will be f mu n and this is minus mu n. So, where n, so let this mass is m. So, one can find the, so this will be equal to mu n and minus mu n, and at x dot equal to 0 or when x dot change its sign. So, this change from minus mu n to plus mu n. So, the system will have a, so the system will have a cubic nonlinearity in spring, and also it will have a nonlinearity here due to this damping. So, this damping force F t can be written as mu n signum x dot. Similarly, we can have some rotor system with or gear system with backlash. So, let us see this system. So, this is a gear system with backlash. One can see the detail of this system from this paper by Siu et al. Published in Mechanism and Machine Theory in 2011, volume 46 and page number 466 to 478. So, here the backlash and clearance is taken into account. By taking the backlash and clearance in a gear system, one can write the equation motion. So, one can write this spring or take this spring as nonlinear springs also. So, one can write the equation motion of the system, and one can solve these equations using the methods studied today. So, next class we will study. So, this finishes the forced vibration in nonlinear systems. So, next class we will study the systems with subjected to parametric excitation. So, in that case we will take few example. So, mainly we will take the example of a sandwich beam subjected to periodic axial load. Then we will take one elastomagnetic system where the system is subjected to axial periodic load in addition to that magnetic field, and third we will take another system with base excited cantilever beam with arbitrarily placed mass, which is subjected to or where we will consider the internal resonance also in the system. So, we will study these three systems in case of the parametrically excited system. So, next three classes will devote to parametrically excited system. Thank you.